Differential amplifier accepts two inputs, subtracts them, and then the resultant is amplified and thrown to the output terminals. So the output of differential amplifier is amplified difference of its inputs. It is an analog amplifier, a direct coupled amplifier. There exists two stages in this amplifier. The two stages are supposed to be identical in all aspects. The transistors that are there in these two stages, they must be identical. The resistors, other components, power supplies, all must be identical in all aspects. That is the meaning of identical stages. These amplifiers are also associated with low noise characteristic or noise cancellation characteristic. In ideal situation, when both the stages are identical, which is impossible in practice, in such an ideal situation, the output is simply amplified difference of inputs. But in practice, in addition to amplified difference signal, there exists a common part of input signals with a little bit of amplification also, that the output terminals. Of course, this is unwanted. From differential amplifier, amplification of difference signal is the only thing that is expected, not common part or common mode of the input signals. CMRR stands for common mode rejection ratio. It indicates how much of the common mode signal is present at the output of differential amplifier. By definition, CMRR is ratio of differential mode gain to common mode gain. In case of ideal amplifiers, ideal differential amplifiers, it assumes infinite value, but in reality, it is not so. It remains finite. Of course, with good design principles, one can make it as large as possible. Multi-stage amplifiers, differential amplifiers, series on semiconductor devices and circuits, lecture number 8.12. Differential amplifiers are direct coupled analog domain amplifiers. There exists two stages in these amplifiers. The specialty of these stages is that they are identical as much as possible. They are major parts, main parts in the structure, in the design of operational amplifiers. They are well known for their low noise characteristic. In the present session, we focus on features of differential amplifiers, their characteristics, their structure, their applications, and other important parameters pertaining to them. Now, a few introductory points regarding differential amplifiers. As already mentioned, they belong to the category of direct coupled amplifiers, like Darlington pair, like Cascode pair. Some more points regarding them we see here. What is differential pair? It is CE added with another CE or CS connected with another CS. In BJT version, therefore, two CE stages, as already mentioned, identical in all aspects as much as possible exists, and in FET version, two CS stages. But here it is required to mention that there is a big difference between differential pair and other pairs just mentioned, Darlington pair and Cascode pair. In Darlington or in Cascode, input is 1, output is 1. Output of first stage goes as input to the next stage. But in case of differential amplifiers, inputs are 2. They accept 2 inputs. They are capable of giving 2 outputs, but usually we take one output, which is the difference of 2 outputs. So huge difference is there between differential pair and Darlington or Cascode pairs. Why differential pair? To prevent a noise amplification that happens in a single stage CE or CS. The function of a differential amplifier is in general to amplify the difference between two signals. Notice why it is called a differential amplifier. Its functioning is it accepts 2 inputs, it subtracts one from the other, amplifies the resultant, and gives it as the output. So subtraction is a synonym for difference, differencing. From differencing, one can implement differential to find differential signal. That's why it is called differential amplifier. Differential amplifier means differencing amplifier. Differencing means subtraction. So subtraction is the operation that is performed by this amplifier. It is the basic stage of an integrated operational amplifier with differential input. It has applications in many physical measurements where response from DC to many megahertz is required. Some more points. Differential amplifier takes 2 input signals and amplify the difference while rejecting their common parts or common levels. This particular point describes completely, totally the functioning of differential amplifiers. There are 2 input modes: normal mode input, common mode input. Normal mode input means differential changes in the input signals. Common mode input means both inputs change levels together. Common means common to both the inputs. Normal means difference, differential changes, different changes in the input signals. A good differential amplifier has a high common mode rejection ratio CMRR of about 10 power 6 to 1 or 120 dB. Common mode rejection ratio is a specification, an important index, performance index pertaining to differential amplifiers. Differential amplifier is supposed to amplify the difference of the two inputs. Not only that, it is supposed to reject completely, totally the common part of the two inputs. But in reality, this common part also appears at the output. It should be absent. Of course, that is ideal case, but in practice, it appears, it is present. Of course, in small quantities. Common mode rejection ratio gives an indication regarding the efficiency of the amplifier in rejecting, in suppressing common part in the signals. Differential amplifiers help us to understand op-amps. Study of differential amplifiers, understanding of differential amplifiers, these are very much essential to understand the design, the functioning of op-amps, because differential amplifiers occupy major role in the structure of operational amplifiers. Some more points. Differential amplifier is the most widely used building block in analog integrated circuit design. Their main advantages are much less sensitivity to noise and interference. So noise and interference, these two are very low in these amplifiers than single-ended circuits. Another benefit is it enables to couple amplifier stages together without the need for bypass and coupling capacitors, such as those utilized in the design of discrete circuit amplifiers. So bypass and coupling capacitors, they become redundant in the design of differential amplifiers. Presence of capacitors in the circuit, they have their own demerits, disadvantages associated with. So their absence naturally implies absence of those disadvantages and demerits in the differential amplifier circuits. Properties of ideal differential amplifier. Input differential resistance, input common mode resistance, differential voltage gain, CMRR. These are the specifications with respect to which a practical amplifier is compared with an ideal one. Notice differential resistance. Resistance offered by the amplifier circuit for difference signal, differential resistance. Common mode resistance, the resistance offered by the amplifier for common mode signal. Differential voltage gain, gain provided by the amplifier for the difference signal. Common mode rejection ratio, it gives an indication regarding how effective the amplifier is in suppressing the common mode part of the input signals. Non-ideal characteristics of differential amplifier: input offset voltage, input biasing, and offset current. In case of ideal amplifier, only these four: differential resistance, common mode resistance, differential voltage gain, CMRR. Only these four parameters are of concern. But in practice, we cannot have an ideal amplifier. What we can have is a practical amplifier. Practical or real amplifiers are associated with these issues. Input offset voltage. What is this input offset voltage? The differential amplifier is supposed to give zero output when the inputs are same. When the two inputs are equal, output should be zero, but it doesn't happen in reality. Even when inputs are equal, same, output exists. It is due to input offset voltage. Similarly, another practical problem is input biasing and offset current. So if the amplifier is an ideal one, these are the characteristics or specifications of concern. In case of practical amplifier, these two also are to be of serious concern for a design engineer or for a end user. Some more aspects one has to look into while studying a differential amplifier or differential amplifier with active load. Its performance when the load is active, and also frequency response of differential amplifier. Amplifiers are designed using transistors, BJTs or FETs. They are associated with the junction capacitances. So amplifier circuits, they are with the reactive elements, reactive components. Of course, junction capacitances are not visible. The presence of reactive elements in the circuit naturally makes it performance or response dependent upon frequency. So frequency response is an important aspect because performance gain of the amplifier now is dependent upon frequency. While putting a differential amplifier into use, we have to take note of its frequency response too if we want optimum performance from it. Here are shown differential amplifiers. First one is PET version, second one is BJT version. Two stages one can see. As already mentioned, the speciality is that these two stages should be identical as much as possible. It implies RDs should be identical. Their resistances, their power dissipation capabilities, everything should be identical. Similarly, Q1, Q2, these two transistors must be identical. But in reality, that level of identity or equality is not possible. But we begin the study assuming that both stages are identical. RD in the first stage is identical with RD in the second stage. Transistor Q1 is identical with Q2. Notice two inputs are there, VG1, VG2. Two outputs are there, VD1, VD2. If one wants, one can take VD1, VD2 separately, but usually while BJT is working, the output is between VD1 and VD2, single output. single output, two inputs, single output. In diagram 2 is shown BJT version. Here also Q1 is supposed to be identical to Q2. RC connected to Q1 must be identical with RC connected with Q2 for best performance. But in reality, as already mentioned, two identical components devices are not available in practice. Now, a few mathematics. In case of ideal differential amplifier, the output V0 is given by V0 equal to EAD V1 minus V2. V1 is input to one transistor, V2 is input to another transistor. Output depends upon difference between these two because it is differential amplifier. AD is proportionality factor. It is gain of differential amplifier. It can be seen that any signal which is common to both inputs will have no effect on the output voltage. Notice here this particular expression, statement, mathematical statement can be considered as the defining relation, defining expression of an ideal differential amplifier. In practical differential amplifier, in general, the output V0 depends not only upon the difference signal Vd of two inputs, but also upon average level called common mode signal Vc, where Vd is equal to V1 minus V2 and Vc is average of V1 plus V2. The output of the amplifier can be expressed as linear combination of two input voltages V0 equal to A1 V1 plus A2 V2. Here A1 A2, these are voltage amplification from inputs 1 and 2 to the output under condition that input 2 1 is grounded. But V1 is Vc plus half Vd and V2 is Vc minus half Vd. Combining this relation results in V0 equal to AdVd plus ACVc. Here, Ad is half A1 minus A2. It is voltage gain for difference signal, and AC is A1 plus A2 is voltage gain for common mode signal. Clearly, it requires to have Ad large ideally, and AC ideally should be equal to 0. Here is given a definition for common mode rejection ratio, CMRR. It is figure of merit for difference amplifier. It is defined as AD by AC, differential gain by common mode gain. Symbol is rho. It is possible to express the output voltage of amplifier in terms of CMRR. A0 is AdVd multiplied by 1 plus 1 over rho multiplied by Vc over Vd. From this equation, it can be observed the amplifier should be designed so that rho is large compared with the ratio of common mode signal to difference signal. Now, we consider mass version of a differential amplifier. So far, we considered general treatment, which is applicable both for mass differential pair and also BJT pairs. Now we focus on mass differential pair. Differential gain is considered first. Vg1 is equal to Vcm plus half VAD. Vcm means common mode part in the input signals. VID is differential part, difference part. Vg1 is Vcm plus half VID and Vg2. Vg1 is input to transistor Q1. Vg2 is input to transistor 2. It is Vcm, common mode part minus half VID. G, here G stands for gate. Input is being given at the gate terminal, so Vg1, Vg2. Output voltages for two individual stages are. Notice these output voltages pertain to AC or signal. V01 is minus GM VID by 2 into RD. Similarly, V02 is GM VID by 2 RD. Corresponding gains are minus half GM RD. In this case, in the second case, it is half GM RD. So differential gain is V02 minus V01 by VID. This is the output, this is the input. Net result is differential gain is GM RD. Notice the expression derived for differential gain assumes identical stages, but in reality, story is different. Identical resistors, identical transistors, we cannot have. Even they are made simultaneously, manufactured, fabricated simultaneously in the same foundry. No two devices can be identical in their behavior. A difference exists. It may be small, but difference exists. Here we consider effect of RD mismatch. Let us suppose RD is RD in one circuit and RD is RD plus delta RD in the other stage. In such case, it can be shown ACM. Common mode gain is V0D by VICM. It is equal to minus delta RD by 2 RSS. Here notice this RSS is internal resistance of the current source that is connected to source terminals for biasing purposes. And of course, it is supposed to be infinity, but in practice, it is not so. For ideal current source, internal resistance should be infinity. Here also, it should be the same. RSS should be infinity, but that is ideal. In practice, it is not so. AD differential gain, it is, we have already seen, minus GM RD. ACM can be expressed as minus RD by 2 RSS delta RD by 2 RD. So CMRR is AD by ACM mod. It turns out to be 2 GM RSS by delta RD over RD. So RD mismatch leads to a CMRR, which is no more infinite. Now we consider the impact of non-identical transistors in the circuit. When transistors are not same, not identical, then their GM values, they differ. Let us suppose one transistor is having a transconductance value of GM, another having a transconductance value of GM plus delta GM. In such case, in what way this difference in the transistors impact the CMRR of the amplifier? This aspect is considered here. It can be shown ACM, gain of common mode signal, equal to minus RD by 2 RSS delta GM by GM, and difference signal gain is minus GMRD. This is already, we have seen it. Now CMRR, it is the ratio of AD by CM. It is 2 GM RSS by delta GM by GM. Notice when transistors are identical, then delta GM becomes 0, CMRR tends to be infinity, which is the case of an ideal op amp where transistors are identical. Next, we consider BJT differential pair to find its differential gain. Let us suppose VB1 is VCM plus half VID, VB2 is VCM minus half VID. See, VCM is common mode part and VID is differential part. VB1, this is input given at base of transistor 1. VB2 is input given at base of transistor 2. Output voltages for two individual stages are V01 minus GM VID by 2 RC. V02 is GM VID by 2 RC. Corresponding gains are V01 by VID equal to minus half GM RC and V02 by VID equal to half GM RC. Differential gain then is V0D by VID equal to V02 minus V01 by VID. It is GMRC. When resistance is there in the emitter leads, AD becomes RC by RE plus RE. Effect of RC mismatch. For optimum or ideal functioning of a differential pair, RCs, collector terminal resistances, they should be identical in the pair, but in practice it is not so. When they differ, resistances of RCs differ by, let us say, delta RC. Then what happens? In what way this difference is going to impact on CMRR? ACM, common mode gain, is V0D by VICM. It can be found equal to minus delta RC by 2 RE. AD differential gain is, we have already seen, minus GMRC. Notice here REE is used. What is this REE? It is bias source resistance. This source is connected to common emitter terminal. ACM can be put in a slightly different form as minus RC by 2 REE delta RC by 2 RC, and CMRR can be computed. It can be found equal to 2 GM REE by delta RC by RC. Notice when delta RC is 0, when resistors are identical, then CMRR tends to be infinity. When transistors are different, then what happens? Their GM values differ. When difference in the GM values is delta GM, then it can be shown ACM, common mode gain, is minus RC by 2 REE delta GM by GM. Differential gain can be found, already found, equal to minus GMRC. So CMRR becomes 2 GMREE by delta GM by GM. Here also one can notice when transistors are identical, exactly same, then delta GM becomes 0, CMRR tends to be infinity. With this we come to the end of this session. In the session, differential amplifiers are introduced, their important properties are mentioned, their functioning is described, and the result of non-idealness in the actual circuit It is also discussed. Hope this session is useful to you. We meet again in another session with a new topic soon.